Okay, so thanks for reminding me. Okay, so Collins, are you okay?
Yes, please, I'm okay now.
So if you generate the log values and you think it will get you confused, just drop the raw values and leave only the log. And how to drop it is what you just type drop, then you select the raw values, then you drop it. It will drop or it will be deleted and leave the log values there. Think there's a question. Yes, I'm already. Yeah, now we are recording it. So can we continue? Okay. So, like we explained in our previous session, if you are dealing with a panel data set, you have to tell Stata that I'm working with a panel data set. If you are working with a time series data set, you have to tell Stata that I'm working with time series data set. And our data is Benin, Burkina Faso, Cape Verde, Cote d'Ivoire, Gambia, Ghana, Guinea, Guinea-Bissau, Liberia, Mali, Niger, Nigeria, Senegal, Sierra Leone, Togo. So they are West African countries. We are studying multiple entities for a longer period of time, which is from 2000 to 2001. So it gives us a time series. And Gabby explained that for time series, we use the X and T. X represents the cross-sectional component, and then the T represents the time series component. So you have to set panel structure, or you have to tell Stata that I'm working with a panel data. And we also learned from our previous session that you see the country and the code, they are strange. And Stata does not accept strange values. Like this one, you see it is in red color. The code is in red color. So we have to encode or recode the strange values, which is either we can use the country or the code to code it numerically so that we can use it to set our time or to set our panel structure. So we will recode the country using the command encode. So encode country, it means that change country to a numerical form. You see, it's already in strange like alphabet. So encode means convert the country to numerical form and name it country ID. So that's the meaning of this code. So encode country, generate country ID so that we can use it to set our time. So you see, I've run it and now we have generated a new variable called the country ID. Let's view it and see. So we see that now it has turned to blue. The blue means Stata will recognize it. Stata will recognize it, but previously it is red. It means Stata is seeing it as a strange value. So let's see code book. So realize that the country ID, please hope you all know code book. I don't want us to go back too much. If not, we will not move forward. That's why. So code book, we have already explained code book in our previous session. That code book is used to show how the data has been coded and what is inside the data. So we realize that for the first country, it is strange. The data type is strange. So strange means it is alphabetical and Stata will not recognize it. And the new one we encoded, the data type is numeric. So numeric, Stata will accept it. If you don't have this one, then you can't set your panel structure. So now we have our country ID. You set your panel structure, which is XT set. The X represent the cross-sectional component, which is the country. That's what we just created. The what
Kenya. Hmm. I said,
Yes, please.
please, nyabotra kakra. And then we'll go see.
Oh, but this one, I
Uh,
thought we have already done it too. Because so I thought we would just move. Then when we get to okay, you
uh,
see, Gabby explained this to us. The XT, we have the time series and the cross-sectional component. I think I'm even the one who explained it. Cross-sectional is where you are studying only a single entity. Like let's say we are studying Ghana for a longer period of time. It gives us a time series data. And then a panel data combines both cross-sectional and then the time series data. Cross-sectional is where you are studying multiple entities at a single point in time. So there's no time, but more entities. That's cross-sectional. So maybe you use questionnaire to collect data from a lot of people. There's no time attached to the data because there's only one time period. It shows that uh, you are dealing with a cross-sectional data. But when you are studying only one entity, with a longer period of time, it means you are dealing with a time series data. So when you combine these two, a cross-sectional data and a time series data, you get a panel data. You get a panel data. So a panel data have the X component and the T component. X represent the cross-sectional, the T represent the time series. So in this study, we are studying more countries, like 15 countries with 25-year time period. So we combine the two to give us a panel data. So when we are telling STATA that we are working with a panel data, we have to use the XT set. XT set. So XT, the X represent what? Collins. What does the X represent? Collins. What does this X represent?
no, and the T is the time series.
The
The
X
T is the
represent
time
what?
series.
He said the
Please,
X
can I be
represent,
heard?
yes.
Yes. I mean the S is the panel and the T is the time series. So
Anyone to help Collins? What does the X represent? Anyone to help? I want to know if you are following. What does the X represent? Collins got the T right, so I want the X. What does the X represent? Oh. Parquesitaria, what does the X represent? This is the fundamental of all the analysis we are coming to do, so you have to get it right before we continue. Parquesitaria, what does the X represent? Anyone to help us? Okay, so I said the X represent the cross-sectional section of the data. The cross-sectional and the cross-sectional are the individual entities. And the T represent the time series. So when you combine the cross-section and the time series, you get the panel. So X, that's why you write X set, country, and then year. So country first and then the year. So X cross-sectional, S comes first, so the country ID comes first. Before the T, then the year comes. Then you run it. So you see that Stata says that panel variable. Now, Stata know that you are working with a panel variable, country ID, strongly balanced. Strongly balanced means the data, we have a balanced panel data. It means all the years are equal. Every country have the same year period. If some countries are having a shorter or a longer time period, you have unbalanced data or strongly not balanced. But this one is a balanced panel. and the year starts from 2000 to 2001. 1 unit difference. 1 unit difference. Okay. So in our analysis, the pre-estimate, we have the descriptives, which is the summary statistics, mean, standard deviation, maximum, minimum skewness, and then the JB. JB is Jack Bearer. That's what we use to test for normality. And then the ketosis. So I think I will try to incorporate AI into it so that you will know how to use the AI for the data analysis. Because the session was data analysis and artificial intelligence incorporation. I think after yesterday lecture, someone told me that we said we will use AI, but we didn't use AI. So I will try to incorporate AI into it so that you will know how to use AI with it. Then summary. So the first analysis in our study is summary statistics. So summary statistics, you use the summarize. You can use the sum or the summarize. So sum, then you select all your variables, which is GDP, CO2, PM 2.5, nitrous oxide, health, exchange, money, and then inflation. So our dependent variable is GDP, independent variable is CO2, PM 2.5, nitrous oxide. Our moderator is health, and then control variables are exchange rate, money supply, and then inflation. So you use the sum, then you run it. So you see, we have the mean, standard deviation, minimum values, and then the maximum values. So, or you can use the same thing, and then you write comma details or comma detail. If you add the comma detail, it will give you a detailed summary statistics, which includes variance, skewness, ketosis, and then the mean, standard deviation, the max, and then the standard deviation. Yes. So you have it. So this is the detailed summary statistics. If you don't add the details, you will get this one. If you add the details to it, it will test the ketosis, skewness, and the variance for you. So that we have commands that we use to export this into a tabular form, but the commands are very complex. The commands are very complex, and right now I don't want us to go there so that we will get confused. So you can copy this data and take it to Excel. You can copy this table and take it to Excel and paste it. You have your result in Excel, and then you arrange it the way you want. Or as modern as it is, you can copy this result and give it to your any form of AI that you are using. Why is this thing to worry me at the top here? You come down here. Okay, so you can, let me see if my AI will open. So I can just ask AI to summarize my result into my data for me. Or you can also use the short approach by giving it to STATA. So summarize this summary statistics in a table for me. The table should have and what we are looking for is here. The mean, so you can write it. I think you have not tested for Jack Bearer. Oh, sorry. I've not given the result to it. So this is different ways you can use to export your data, or you can also take it to Excel. The Excel, when the result is scanty, then you get problem with it. So try to make use of artificial intelligence. That's why I said this study will incorporate both so that we will know how to deal with it. Please, you can use your ChatGPT or you can use your so now I have my results in a data form. I'll copy it, I'll come here and I will insert it here and then format it. If you have any question to please you can ask. So now I have my result in data in a table. You see it's looking very nice. Then I can format it. This is how we present it in manuscript. So all that you are doing is how you present it in a manuscript. So maybe summary statistics. And you can use the APA formatting style. Mm. So I can close the gap a bit. This thing, some people really struggle a lot. You can just edit it like this. And I will not do this formatting again. So learn it right now. Now I'm done with the formatting. So now I have my mean, standard deviation, mean, max, skewness, and then my ketosis. Note, I use ketosis instead of ketosis, which is a metabolic. All form is not necessary. That's AI note. All values are rounded to 2 decimal places. So that one you can give the command that use 3 decimal places or use 4 decimal places. That's fine. But we mostly use 3 decimal places. I didn't check it. That's why it used 2 decimal places. So that's fine. I think we skipped the Jagbera, but we will test it. I will not edit the tables again. So I think so the summary statistics, we have the normal one without the, oh, okay. This is using the raw values. And I dropped the raw values. So let's use this one. Mhm. So this is the one we created. You can add the details to it. And now you have it. You see this form, you can easily copy this and paste it into Excel and easily edit it. But you see this form, it is unstructured. So this one, if you copy it and go and paste it into Excel, it will take a lot of time to restructure it into this form. That's why it's better to make use of AI now because you work hand in hand with it. And now let's do the normality test, which is the Jagbera test. It's part of the summary statistics. It's part of the summary statistics. So Jagbera test, we use it to test whether our data is normal or not. You just type JB. And please, if you run any command and it does not respond, me, I've run it before, so I've definitely installed those packages. So if you don't have the JB package, just type SSC install JB and install the package before you run it. I already have it. I already have it. You see, all files already exist and are up to date. But if you run it and it does not respond, or they say JB is not recognized or JB unrecognized, it means you have not installed it. You have to install it using this command. So JB GDP, Jagbera test GDP. And please, some of us, we have done a little statistics. Let's try to interpret this. So you see the Jagbera normality test. Jagbera normality test, HO. The HO is the null hypothesis. And we know that null hypothesis normality, it means that null hypothesis assume that the variable is normal. The variable is normal. That's the null hypothesis. Then we use the p-value or the chi-square test to check the normality. If the value is less than 0.05, it means we reject the null hypothesis. That's a bit statistics. And that's what you will use in every field. If your p-value is less than 0.05, We have the 10% threshold, 5% threshold, and then the 1% threshold. Mostly in social sciences, we use the 5%, but you can still use the 10%. But 10% is a weak significance. 5% is a moderate significance. 1% is a strong significance. So 0.03 is less than 0.05. That means it is moderately significant. And if it is significant, we reject the null hypothesis. And what does the null hypothesis say? The null hypothesis says that the variable is normal. That's there's normality of the variable. And if you are rejecting the null hypothesis, it means the variable is not normal. Please, do you understand? Or I'm moving fast. So the test, this is very important for all kind of analysis that we are going to do. How to explain the p-value or the null hypothesis. If you're able to understand the null hypothesis, you will be able to do all kind of analysis. So understand it from here. Always check the null hypothesis. If the null hypothesis says that there's normality and you check it and it is less than 0.05 or less than 0.01 or it's less than 0.1, then it means it is we reject the null hypothesis. So all these, from what I'm seeing, all of them are not normal because they are all less than 0.05. So our variables are not normal. It does not follow the normal distribution. So let's give it to AI to interpret it and let's see. So we are trying to use two birds to kill one stone. Let's see what AI will say, whether it is. So the bottom line, none of your variable follows a normal distribution. How to the Jaguar test checks if your data is normally distributed. When the p-value, the number on the right is less than 0.01, it means that the data is not normal. Yes, like we said, if this value is less than 0.05, it means it is not normal. It is not normal. Okay, so we can I can ask AI add the normality result to the table one or to the summary statistics table and make it 3 decimal places. Always after AI creating your table for you, you can cross-check the values because AI is prone to hallucinations. So it's always important to cross-check your values unless you are using a premium version. Okay, so now we have the normality here. The normality is here. The normality is here. Or I can ask AI to represent the p-value with sig sign, which is asterisk to the JB test. That's how we present result significance level in. Yes. So you see that I've changed the p-values to asterisk. So 3 asterisk means it is less than 0.01. 2 asterisk means it is less than 0.05. 1 asterisk means it is less than 0.1. Prince Nyako, please, you can talk.
Yes. So I know that no I know that economic data, for example, the GDP and real world data sets after you doing the Jaguar test not get normal distribution. It will not be normal. So what happens if I pick a data from somewhere and I do this test and, for example, GDP gives me normally distribution? What should I do?
Oh, these things, you are doing all these things just that so that if someone is interpreting your final result, the person will consider all these factors. So if your data is skewed, if someone is interpreting your results, the person will factor that into
Hello.
the interpretation. It does not mean that if you get your variable is normally distributed, you cannot use it, or if it is not normally distributed, you cannot use it. Each of them you can use it, provided your data is genuine. You have not manipulated the data in any way. If it is whether normal or abnormal and it is genuine, you have not manipulated it, you can go ahead to do your analysis with it. But you have to disclose it. You have to present it as it is, whether you had a normal or not normal, so that anyone interpreting your result will factor that. So your standard deviation is not like it is going to, if your standard deviation is high, don't stop your analysis or something, or it's low. It means that if we're interpreting the result, you factor all those results into it. Oh, okay, maybe it's because the data was skewed. That's why it is that. Or it will give a general knowledge of the data. So the summary statistics is more of giving a general overview of how your data look like. It's not like if it is that, you can't use it. No, that one we have not gotten there yet. Please, that okay.
Okay.
So whether it is normal or
Yes.
abnormal, provided you have not touched the data, then you are good to go. And this one too, some people prefer to present both the raw values and then the converted values. That one too is fine. But nowadays, even the reviewers, they have lost interest in these summary statistics. So if you provide a lot of tables too in your work, it will give you problems. So you can choose to present the converted one, especially if you are using the converted one for your analysis. It's better you present the summary statistics of the converted data so that you know the kind of data you use for the analysis. Please, that okay?
It's what?
Yes, please.
I want to see the Jangbera, this one, the command again.
The Jaguar is just JB. JB. Then you add you select your, so you just type JB. JB, then you select the variable, then you run it. But as I said, if it's
JBK.
not coming, you have to install it using the SSC install JB.
She.
Hmm.
Bukechi.
Okay, so we are done with the summary statistics. This is our summary statistics table, and this is exactly how you can present it. You can present it in this way. Don't forget the note under it under your results, because if you forget it, the reviewers will bring it back and ask you to include it. Explain what the 3 stars represent, the 2 stars represent, and then the 1 star represent. Where's my 1 star? To 1 star to all variables reject normality. That one self is not even important because you explain it in the. This thing is not important. You explain it later. So significance level, explain it. Then let's look at the correlation and then the VIF. And VIF, we have always been talking about VIF. VIF help us to establish whether we have a multicollinearity problem or not. And I think, okay, so our study have moderating variable. Let me explain this. Moderating like this, where is even the conceptual framework that we draw? Okay, so this is the conceptual framework that we are working with. Health investment is the moderator. And how we treat moderator, we multiply the moderator or the moderating variable by each of the independent variable. or the variables you are trying to moderate. So in our case, we are moderating health investment. We are checking the role of health investment in the relationship between all the three. So you have to multiply health investment by carbon emission, multiply health investment by air quality, multiply health investment by agricultural intensification. So this place too, it works the same as the generating the log value. You can multiply it in Excel before you bring it here, or you can generate the values here. So now we want to create the interaction term. The interaction term is multiply your moderating variable by your independent variable. That's what they call the moderation analysis. So you multiply your moderating variable by the independent variable to create one variable, which they call the moderator. Please, are you okay with it? So let's create the moderating or the interaction variable by multiplying our moderator or our moderating variable, which is health expenditure, by each of our independent variable. So just generate here. So you use the same process that we use to generate the logarithm. Generate a new variable called CO2 health, like CO2 times health. You can give it any name, provided you remember that that's how you named it. So me, I'm multiplying two things, which is CO2 and health. So I use natural log CO2 health is equal to CO2 times this asterisk represent multiplication. So CO2 times health. I'm multiplying health by carbon emission. I multiply health investment by air quality. I'm multiplying health investment by agricultural intensification to create our interaction values or interaction variable. The interaction variable is what we use to check the moderating variable or the moderating effect. That's how we treat moderating variables. Mediating variable, we treat it differently. When we get there, we will cross. But today we are dealing with moderator because they steady have a moderating variable. So generate CO2 health is equal to multiply CO2 by health. So let's generate the new variables. So now we have the CO2 health. Let's generate PM 2.5 health. That's PM 2.5 times health. Generate nitrous health, which is nitrous oxide times health or agricultural intensification times health. So nitrous times health. So you see, we have three new variables here. That's what we call the interaction term. The interaction term combines the moderating variable by the independent variable. So that one we have created it. We will use it later. So you can create it from the beginning of your analysis, or you can create it when you get there. Okay. So let's do, I think, next on the list. When we get to the moderation, we will explain it again. So next on the list was correlation and VIF. You can add the interaction to the correlation, but you see, when you add interaction variables to your correlation analysis or to your VIF test, it increases the collinearity. Collinearity is where the independent variables are highly correlated. And if the independent variables are highly correlated, some of the models will drop them. It will give you problems. So let's look at some. So when you are running the correlation, don't include your interaction variable because you have created a new variable from the variables you are already having. So definitely the interaction, the one you have created, will highly correlated with the other variable. So you see the correlation matrix without interaction. I'm trying to explain the correlation, the multicollinearity problem to you to understand. So this is our correlation. We have done correlation more times. So CO2 and GDP is highly correlated because it's having one. PM 2.5 and GDP is having -1, it means they are negatively correlated. So that's how the correlation works. PM 2.5 is negatively correlated with GDP, which is -0.1215. Yes. So that's how the correlation is. The code is just core or correlate. You can just type correlate or core, and then you select your variable. So maybe CO2, PM 2.5, nitrous oxide, health, exchange rate, and then inflation. Then you run it, it will come, your result will come. Your result will come. So, and look at this one. I've included the interaction variables that we created into the correlation. You can copy this table, give it to AI, or you can bring it to Excel, like I explained. You post it into Excel, you have your table already. You have your table here. So you can bring this table into Word, or you can copy it and give it to AI to put it into a table. I said that I will not create a different table again. You can also use the pairwise correlation. The pairwise correlation comes with significance, and that's what some of the reviewers like. They want you to test correlation with significance. If you are testing correlation with significance, you can use the pairwise correlation. So the pairwise correlation is PW core. PW core. Then you select your variables. I don't want to include the interaction variable, so I'm deleting it. I will use it to explain something for you to see what we mean by the multicollinearity. So star 0.5 significance. I'm using 0.5% as significance. Then I've run it. So you see that this one, it comes with significance level. See that you have the 0.00, 0.00 attached. This one is not significant. This is not significant. This is significant. So the pairwise correlation comes with significance, but the normal correlation does not. Okay. So let's run the VIF. Let's run the always VIF. We run VIF after OLS regression. We explained OLS regression the last time that I think I explained it myself. I said the OLS regression is the basic form of regression that you can run. So we use the regress or the reg. You can just type reg, it will come, or the regress, it will come. Always select your dependent variable first. In our study, we said that our dependent variable is GDP. Independent variable is CO2, PM 2.5, which is air quality, and then nitrous oxide. Let me use nitrous. Then we have the moderating variable, which is health expenditure. And then we have the control variable, which is inflation, money supply, and then we have the last one is what? Exchange rate. Please, if you don't understand anything, you just draw my attention. Okay. So these are the variables we are working with. So we have the dependent variable to be GDP, independent variable to be CO2, PM 2.5, nitrous oxide, moderating variable to be health expenditure, inflation, and the money supply. So you run regression with this. So reg, you select first your dependent variable, which is GDP. Then you select your independent variable, which is CO2, PM 2.5, nitrous oxide. Then I want to include my moderating variable, which is health. Then I will select my control variables, health exchange, money, and then inflation. Then I will run it. So you see, we are getting missing values here because our variables are highly correlated. Our variables are highly correlated. R square of 1. Why are we having an R square of 1? It means two of the variables are highly correlated. Okay, let's run the VIF and see. Okay, our VIF is okay. So why, no, the R square is 1. Okay, let's focus on the VIF. We are not using OLS right now. If you're using OLS, I think the CO2 in the data has been, we made an error in the data. The CO2 and the GDP per capita is giving us error because we are having a coefficient of 1. Coefficient of 1 for CO2, which is not supposed to be so. But we are not working on OLS now. So you see that the VIF, we are having 1.95, 1.95, 1.95. We are having, all of them are below 10. So each of them is below 10. If it is above 10, then there's a problem. So let's test the one with the interaction term. So you see this one, I've included the interaction term. So reg GDP there's an error in the data. There's an error in the data. I think we have to fix it before we continue. If you realize the log and the CO2 is giving us the same value. Please hope you can see that. The GDP and the CO2 is giving us the same value. It means we made an error in the data. Let me fix it before we continue. If not, it will give us problems. That's why the correlation was giving us 1 here. That's why the correlation is giving us 1 here. So all those things should be checked. So let me import the data again and let's check why we got that. I think when we're doing the log transformation, there was an error we didn't see. Okay, so I've re-uploaded the data. Let me check. Okay. Please hope you understand what we are doing now. Oh, okay. So you see the gen I used gen GDP and into the bracket I wrote CO2 instead of GDP. So that's why. So let's fix it. So I've generated the logs again. Let me drop all of the raw values. Yes, I think that's where it was coming from. Okay, so I've dropped all of them. So now we have our data. Let's encode it again. So this is why you have to always use the do file. You just rerun everything and you are good to go. So I've set the time. Now let's generate these values again. And let's do the correlation again and see. Yes. So you see that now instead of the 1, it is now 0.8855. Yes. We made an error in there. Now let's run the regression. Yes. So now the regression is working perfectly. It's now working perfectly. So now the CO2, you see that it's significant. But as I said, OLS, we don't use OLS model for publication. So it's used for basic checks. So now always run the OLS, then you type VIF. So we can see that our VIF is stable, is very, very much okay. They are all under 10. Each of them is under 10. But let's see something. If I am running the regression again, and I will include the interaction term that we created for the moderator. So now I've included the interaction term, which is these three: CO2 health, PM 2.5 health, nitrous health. These are, then let's see the VIF. Please, can we see what is happening? Please, who can explain what we are seeing to me? What we are seeing there, someone should explain it to me. Why is our VIF around 300 and something? Samuel Alote, can you explain it to me? Why is our VIF 300? Why are we having VIF of 300? Samuel Alote, today I'm on you. Samuel Alote, where are you? Come and explain it to us. Because here we're having 1.9595, which is very good. But now we are having 300 and something, 86. And I said that if it is more than 10, it is problematic. What do you think is happening? Who will help us? Richard, Wisdom, Prince, Parkwesi, Collins. Hey, my boss is here, Eric. Eric,
Yes,
I
yes.
greet you. Okay, Alote. Alote, why? Why
Ah,
is our
okay.
VF?
I think let me see. You included the moderation effect.
So what do you think is happening?
You included moderation effect, so I think that's what is increasing the multi-linearity, right?
Yes, so it means the variables are highly correlated. We are having a multicollinearity issue because these three indicators was created from the PM 2.5, nitrous oxide, CO2, nitrous oxide, and then the health. So the moderating variables or the interaction variables are highly correlated with the ones we were created from. So the PM 2.5 was created, the PM 2.5 and health was created from the PM 2.5 and health individual values. That's why so they are correlated, highly correlated. That's what we call the multicollinearity issues. So if it is high like this, it means you have a problem. But this is as a result of the interaction term. So when you test your VIF, you don't have to include the interaction term. Just test it like this, then you are good to go. So you can present the correlation results and then your VIF in a table. Today could be today, because our time is far spent. So this is how I'll put my own in table. If you can also adopt your own process. So I want AI to combine both tables for me. So combine both. As we said, we are using AI incorporation in data analysis. So you can use it or you can use the Excel format. Combine both results into one table. Put the VIFs below each each variable. Bottom, is it row or column? Row. Okay, let's see how we will get our table. You can do it in Excel and you can also use this is where AI, it is trying to add it to the summary statistics, correlation and VIF pen and here. I don't need the other ones. It is trying to add the okay. So this is how I want it. Yes, yes, great, great, great. Take advantage of your anticipation. So now we have the summary statistics. I can put my correlation also here. Please hope we are following. Okay, so
Yeah, we are here.
okay. So now we have our correlation and then VIF. So this that when we are done, we will publish it. The one I'm running right now.
Yes, with all of us, our name on it.
We will see. We see what the Holy Spirit will say about it. We will do CCC. Okay, so that's how you see the VIF is below here. So now, so when you pick CO2, the VIF is 1.8. When you pick PM 2.5, this is how I normally present my correlation results. So table 2, correlation and variance inflation factor results. Now we have our 2 tables. So the next one is, no, let's skip this one. This one is too long. We will come to it later. So let's look at the slope homogeneity test. The slope homogeneity test. The slope homogeneity test, we use it to test whether there's differences in the changes in the countries. So whether the countries are different, are they homogeneous or they are heterogeneous? And as I said, every test that you do from here will influence the kind of model you will use, So if you have purpose in your heart that this is exactly the model I'm going to use, maybe you have decided that I'm going to use fixed effect model, or I'm going to use a random effect model, or I'm going to use ARDM, then some of these tests you shouldn't do it. Because if you test slope homogeneity, the result you will get, it has to influence the kind of analysis or the model you can use. Okay, so the slope homogeneity test, I've intentionally skipped the unit root because it's too long. The code is from here. We will come back to it when we are done with the slope homogeneity and then so this is the slope homogeneity test. If you have it, please kindly install it. So the command is xthxt. xthst. So you can do the SSC install. So let's continue, please. If I'm running fast, then you alert me. But I think the pace that we are going is fine. So I've already installed my slope homogeneity test package. So if you don't have it, you can type the SSC install xthst. Then you install it. So mine already exists. Mine already exists. So you can install it. Then you type it and select your variables. You type it and then you select your variables. So let me type it here. So xth st st. Then I select my variables GDP CO2 PM 2.5 nitrous oxide health exchange money and then inflation. Yes, yes. So this one too, let's use the null hypothesis testing to explain the results that we are finding. This is one benefit of using STATA packages. Most of them will give you the null hypothesis before it will give you the result, so that you can use the null hypothesis to interpret the result. So this is Pesaran Yamagata 2008. Please always cite the propounder or those who propounded this method or this test, which is Pesaran Yamagata 2008, Journal of Econometrics. You can go and explain it. So it is used to check the slope coefficients are homogeneous. So the null hypothesis is slope coefficients are homogeneous. Homogeneous means the slope coefficient among the countries. This one we are dealing with countries. So among the countries are the same. Are the same. So we use it to check whether the slope coefficients are the same across the countries or they differ. And the null hypothesis says that slope coefficients are homogeneous. And then we have the p-value, adjusted p-value, and then the normal p-values. So adjusted p-values, we are having 0.004, the three of them. And as we explained, always reject the null hypothesis when the p-value is less than 0.05, 0.01, sorry, 0.01, and then 0.1. So this one, it is less than 0.01, which means it is highly significant. If it is significant, we reject the null hypothesis. And the null hypothesis is saying that slope coefficients are homogeneous. So if we reject the null hypothesis, it means slope coefficients are heterogeneous. So if it is heterogeneous, it means the slope coefficients are different. They are different. So it means the slope coefficients of each country are different. So we have to use a model that accounts for the individual effects. Please, do we understand?
As I said, Mentias you. Much of us will be my
Which part didn't you understand?
With my data, for instance, I'm getting similar results like what you had, but I'm not getting the this one, the adjusted explanation well.
Oh, adjusted is just an adjusted version of the main one. It's like R square, then you have adjusted R square. It's like a robust R square. So this one is a robust delta value. So that one, the adjusted, don't worry about the adjusted or something. You have the p-value. The p-value is less than 0.05, meaning it is significance. And we said that if it's significance, we reject the null hypothesis. The null hypothesis states that slope coefficients are homogeneous. And if
Okay.
slope coefficients are homogeneous, it means what? If we are rejecting homogeneous, it means it is heterogeneous. Please, this hypothesis testing is very important. And if you are not able to get it, then it will be problem for all of us. So please, I beg you, understand how to reject or fail to reject null hypothesis. You see, the first one, when we did the Jagbera test, I explained it, and here too, I'm explaining it. It is 0.00. It means we reject the null hypothesis of homogeneity. And if you are rejecting homogeneity, then what? Heterogeneity. It means the slope coefficients are homogeneous. Please, any question? So it means that if we cannot use a fixed effect model, we have to use a model that accounts for the differences in the coefficient or the differences in the countries. So we can use a models like the mean group estimator, the pool mean group estimator, or the common correlated effect estimator. That's why I said anything that you test will have an impact in your model. So if you run this and you realize that it means that if you test it, that means you have to use the result. If you test it, you have to use the result. Please, any question on the slope homogeneity test?
Hello, sir.
Yes,
Can you
please.
also test it? If it's not favorable to you, you forget about it.
Please come again.
I'm saying that maybe when you test it and it's not favorable to you, can you forget about it and go and do what you originally wanted to do?
What do you mean by it's not favorable? That's why I said you shouldn't have a preconceived model that this is the model I'm going to use. Unless the model is robust enough to account for all those things, like a system GMM model. We have a model we call the system GMM or the two-stage least square method. Those things account for heterogeneity, it accounts for cross-sectional dependency, it accounts for a lot of problems, both co-integration and everything. So if you are using a model like system GMM, there's no need to even do these tests because the model has already been structured for these things, or like a machine learning model. But if you want to use these methods like the panel phase effect, ARDL, VAR, and those things, then you have to test these things to see whether your data is suitable for that model. So if you don't want to test it, then go for a strong model like the system GMM or maybe the instrumental variable approach. Those ones are already built for these things. If you skip this one, then you go and run fixed effect model. A reviewer can give you problem. A reviewer can give you problem that, hey, why are you using a fixed effect model? Are you sure your study is having a heterogeneous or a homogeneous relationship? Please, do you understand?
Yes, I get it. Yeah.
Okay.
Thank you.
So if you don't want to have any problem with any reviewer, then so that's it for the slope homogeneity test. Okay, so you can present it. This one there, I will not give it to AI there. Let me see if I can give it to STATA to do it so that we will know how to. Oh, this thing too is worrying me. This, hey, how do I even hide it? Okay, so okay, let's see. Hey, why is it? Okay, let me put this one here and put so you can also edit it in how do we call it? You can edit your table in Excel. But for me, if I want to be fast, I will just take it to AI to do it for me. Then I'm good to go. These things are not important. These things are not important. Okay. Okay. Then I'll come to it and present it here. So if you have those who will be doing for those who have 2 or 3 models, like your dependent variable is 2 or 3, you run the same thing twice for each of the dependent variable. So please take note. If your dependent variable is 2, it means you run the model with the first dependent variable, then you run the result or the test for the second dependent variable. So each of the tests will be done twice. That's why sometimes it's preferable to use just one dependent variable. Because if you have multiple dependent variables, it means all your tests will be done twice. So now I have my table for slope homogeneity.
Yes, sir.
Yes, please.
Can you repeat that part again?
Which part?
Uh, the one you said if you run something, if you
Okay, you
have
are
two
not paying
independent variables.
attention. So let's say I have 2 dependent variables. If I have 2 dependent variables, let's say GDP and then what again? Maybe GDP or okay, let's say maybe GDP and CO2 are my dependent variable. So I will run the first one with GDP as my dependent variable. Then the second one, I will use CO2 as my dependent variable. So I'll run it twice. Do you understand?
Yeah, I get it now.
So yes, you run each of the model twice. So the slope homogeneity, you test it for the first one and see. Then you test it for the second one, or you can choose to use just one dependent variable. And the same thing applies to the cross-sectional dependence.
Okay.
Okay. Please, any other questions? So as I said, this one, we are having a significant, that means our individual countries are heterogeneous. So we have to go for a model that accounts for that heterogeneity. And sample or example of those models are the pool mean group, and then the mean group estimator. We have the common correlated effects estimator. That one to account for slope heterogeneity. Okay.
So the last model,
Which last model?
the
The
one you just mentioned.
common correlated
Who?
effects, CCE.
Okay. Okay.
Okay, so let's continue. I think our time is almost up. So today, maybe we'll continue some other time. So let's try and see if we can finish the cross-sectional. The cross-sectional dependency test, we use the XTCD2. It's also developed by Pesaren. Please, as I said, always cite the propounders in your work. Like the slope homogeneity, it was propounded by Pesaren, Yamagata, and then, yes, Yamagata 2008. So you have to look for this work and cite it. And state that you use the Pesaren Yamagata test. Because we have a lot of tests, so you have to specify the kind of test you used. And then this one too was done by the same Pesaran. But I think this one, Yamagata was not part. Pesaran did it alone or developed it alone. So that one too, we use the XTCD2. We have other ones too that you can use. When you go to eViews, eViews also have a different packages that you can use. Even in STATA, we have a different packages that you can use. But the one I work with or we mostly work with is the Pesaran 2015, which is the XTCD2. XTCD2. So you XTCD2, if you text it and it's not coming, you can install it again or you can install it. So you first select your dependent variable, which is GDP, independent, which is CO2, PM2.5, nitrous oxide, and then the moderator, which is health, our control variables, exchange rate, money supply, and then inflation. Then I've run it. So this is the result. So testing for weak cross-sectional dependency. This is the last time I will be explaining this hypothesis. So testing for weak cross-sectional dependency, CSD. You have the null hypothesis and then the alternative hypothesis, which is H0 and then H1. The null hypothesis is weak cross-sectional dependence. It means the model already assumed weak cross-sectional dependency, or like there's no cross-sectional problem. H1 state that there's a strong cross-sectional problem. Cross-sectional is like the companies, or sorry, the countries influence each other. If something happened in one country, it will have an impact on the other country. So they are dependent. So if something, we are dealing with CO2, it means when CO2 is going up in Ghana, it will have some impact in the other countries we are working with. That's the cross-sectional dependency. So cross-sectionally, they are dependent. So we are testing, is this dependency strong or is weak? If it is strong, it means there's a presence of cross-sectional dependency. That means you have to use a model that addresses cross-sectional problem. If it is weak, it means that there's let's say there's no presence of cross-sectionality. Then we can go for a normal model, a static model, or something that have no relationship with cross-sectional. But if you test and you see that there's a strong presence of cross-sectional, that means you have to use a model that have a strong cross-sectional problem. That accounts for a strong cross-sectional problem. So you see that we have a 4 test here. We have 4 different tests here. CD, CDW, CDW plus, and then the CD asterisk. And each of them has been explained here. CD is Pesaran 2015 and Pesaran 2021. CDW was developed by Geodis and Rees. CW Plus is Power Enhancement from Fan et al. 2015. And then the CD asterisk is Pesaran and then Shear. I think it's a Chinese name. So always use the p-values to determine. You see the H0, the weak hypothesis. The null hypothesis states that weak cross-sectional dependency. That means let's say there's no cross-sectional problem or there's not much cross-sectional problem in the data. And if you have a significance, you see that all the 4 tests have significance, which is all of them are less than 0.05. So it means we will reject the null hypothesis. What does the null hypothesis state? The null hypothesis states that there is weak cross-sectional problem. So if you are rejecting the null hypothesis, what does it mean? Someone should explain it for us. If you are rejecting the null hypothesis, what does it mean?
Okay, so it means that there is strong cross-sectional dependence.
Hallelujah.
Amen.
So, so that's it. It means if you reject the null hypothesis of weak cross-sectional dependency, it means there's a strong cross-sectional dependency problem. And if there's a cross-sectional problem, it means you have to go for a model that addresses a cross-sectional problem. So we can we can use the common correlated effect or the Discord-Cray model. But Discord-Cray recently realized that there's some of the reviewers who was making strong arguments that it does not address all cross-sectional problems. But I think we have used it before and it was accepted, so you can use it. Because this could create adjust the cross-sectional dependency issue. So that one too, you can use it. And then the common correlated effect too, you can use it. And I think we have cross-sectional ARDA. Yes, we have a model like that, cross-sectional ARDA. So if you test for slope homogeneity and there's a presence of slope homogeneity, you also test for cross-sectional dependency and there's a presence of cross-sectional dependency. That means you have to use a model that addresses both. And we have established that the CCE model addresses slope homogeneity. You have also said that that model addresses cross-sectional dependence. That means if you're having both problems, you can use the CCE model, or maybe the pool mean group model, or maybe the cross-sectional ARDL model. And here we have also seen that the Discord addresses the cross-sectional problem. But that one I have to find out whether Discord addresses slope homogeneity problem. I think one of my works, one of the reviewers raised that point that we tested slope homogeneity and there was a presence of slope homogeneity and we used the Discord method. Why didn't we factor the slope homogeneity? So that one we have to find out together whether Discord addresses, but I know that it addresses some level of cross-sectional dependency. But I will find out whether it addresses slope homogeneity. So if you want to use Discord method, then for now, I will advise you not to test for slope homogeneity. Test for only cross-sectional dependency. Unless when you test for slope homogeneity and you see that there's slope homogeneity and not heterogeneity, then maybe you are good to go. Please, are you okay with the cross-sectional dependency? So we realize that all of them. So this one, okay, so this one is insignificant. It means the last one is having insignificance. That means you fail to reject it. But since 3 of them are having significance, we will go for the 3 instead of the 1. So we can see that it's having a mixed result. But since the majority is having significance, then we'll go for the majority. So all of them, so let's see if AI will support our interpretation.
Set. So
Yes,
what
please.
if 2 of them were supporting and 2 of them were against?
And so you
What would you
explain
do?
that you have a mixed cross-sectional dependency. It means there's some level of cross-sectional problem. There's some level, so just explain that you have a mixed result. So there's some level of cross-sectional in the problem. So you have to use a model that addresses it. So you see,
Okay.
this checks if your panel data has cross-sectional dependence. That means whether what happens in one country affects others. So are the countries connected or not? That's what the cross-sectional dependency does. So the CD test, Pesaran, almost everything shows strong dependence, like we said earlier, because the p-value is 0.00. Only exception in health. Okay, so health was showing a weak dependence. For only the CD test, the CDW, you see, they have written here mixed results. Mixed result means that in GDP and money, it shows dependence, others are borderline. Just explain it that you're having mixed results. But since it is mixed and some of the models are showing dependence, you can go and look for a study which they also had a mixed result and use it to back your explanation. Always back your explanation with empirical study so that you will not find yourself wanting. And it says that you have the data shows a cross-sectional dependency. This makes sense because countries influence each other through trade policy. So West African countries will definitely be cross-sectionally dependent because whatever is happening in Nigeria will affect Ghana through ECOWAS and the trade route and others. So standard panel regression methods like fixed effect assume independence across units. your data violate this, you will need to use methods that account for cross-sectional dependency. So you can use the score cree, the panel corrected standard error, common correlated effect estimators. Yes. So you have to use models that addresses cross-sectional problem, like what is listed there, the score cree, panel corrected, and then the others. Okay, so let's look at, I think we have to be getting ready to close. Let's test co-integration before we test the unit root, then we close. I'm not sure today, we'll test the main estimate today. So co-integration, please, any question? Any question?
Hello, Zinase. Hello.
Hello, boss.
Yes, our boss. I wanted to find out. So, in the case where we tested for the slope homogeneity and uh, what do you call it, the cross-sectional dependency, do we have a model that will seek to correct the two?
Yes, that's why I said the CCE does that. Because I said
Okay.
when we tested the slope homogeneity, I said because of the presence of heterogeneity, you can use the CCE model. And when we tested for the cross-sectional too, I mentioned the same CCE model. So I think CCE
Okay.
model and then cross-sectional ARDL, there are a lot of models that addresses both. There are a lot of models that addresses both. And one is the CCE
Okay.
model. I think cross-sectional model also does that. And then I think the Pullman group estimator also addresses both. So you can use any of them. You can also go for the system GMM. System GMM also does that. And I think this two-stage least square also does that. And then there are a lot of models that addresses both. Okay.
Okay. Thank you.
Okay, boss. Please, any other question? Okay, so let's continue with the co-integration test. Oh, the cross-sectional, let me present the results. Let me present the results. Maybe when we are done, I will give it to someone to interpret it so that we publish it again. Hey, no, this study has been published, but I think the one we published, we use machine learning model for it. So maybe we can do it using econometric model. So you can also do the same. You can use your AI to put your result into a table. Yes, you can do that. That's what I use now. Previously, I used to use the command, and you write command, long command, and it will even be giving you errors. So now I just prefer using my AI to do it. Collins, after the analysis, then you see me. You come for it to go and interpret it. Cross-sectional dependency test results. Yeah, so the citation, don't forget to cite it in the main interpretation. So you can choose not to include it here, but it's fine. You can do that. So now I have my cross-sectional table too. So let's look at co-integration. The co-integration, we have different forms of co-integration. We have the first generation and the second generation co-integration. The first generation is used when there's no cross-sectional problem. That's why always you have to test your cross-sectional dependency before you do the co-integration. If you test it and there's a co-integration problem, or sorry, if you test it and there's a cross-sectional problem, then you have to go for the second generation, which is Westerland. So you have the Westerland co-integration test, Pedroni, and then the cow co-integration. Westerland, Pedroni, and then the cow co-integration. So if there's a presence of cross-sectional dependency problem, you have to go for Westerland. But Westerland, I don't know. I've run Westerland like 50 times. I've never gotten co-integration before. I don't know why. So what I always does it, I will run the Westerland and then I will run the first generation, which is the cow and then the Pedroni to support it. And I will have a studies that use this both to do it, although there was a presence of co-integration. But on the surface, when there's a cross-sectional problem, use Westerland co-integration. But I don't know if it's me alone or you can also go and try it. Maybe you have to test it in eViews 2 and see. Because always, anytime I run Westerland, either I get problems or I get no co-integration. Co-integration is used to test the presence of long run and then short run relationship. If you test co-integration, you are checking whether there's a long run relationship between the variable, between the independent and then the dependent variable. That's all the co-integration test is. So if you do the co-integration and there's a presence of co-integration, it means you have to use a model that estimates long run and short run relationship. If you test it and there's no co-integration, it means you can use only a short run model. It means you can use only a short run model. But if you test it and there's a presence of co-integration, it means you have to use a model that tests for both long run and then short run model. So let's use the power co-integration. So you use the XT co-in test. And the XT, we have explained what the XT. So realize that all the models, there's XT in front. All the models, there's XT in front. The XT represents the panel structure of the data. The panel structure of the data. So we have the XT co-in test, like co-integration test. So XT co-integration test. Then cow GDP, then I'll select my variable GDP, CO2, PM 2.5, nitrous oxide, health, exchange, money, and then inflation. So you realize that all of them are significant. Let's look at the null hypothesis. This one, someone should explain it for me. Who will volunteer to explain the result for me? Is there presence of co-integration or is not, based on the null hypothesis? Someone should explain the result for me. A volunteer.
Okay. Seth, let me try.
Okay, sure.
So the null hypothesis says that there's no co-integration.
Okay.
The p-values are showing that they are significant, so we need to reject the null. If we
Okay.
are rejecting, then it means there is the presence of co-integration.
That's it. That's it. That's it. That's it. Yeah, good. So it means that there's a presence of co-integration because the null hypothesis is saying that no co-integration. And the alternative hypothesis says that all panels are co-integrated. And if the null hypothesis are saying no co-integration and the p-value is significant, we reject the null hypothesis and go for the alternative hypothesis, which is panels are co-integrated. So we reject the null hypothesis of no co-integration and go for the alternative hypothesis, which says that there is presence of co-integration. And this one, we are even lucky. All of the tests are showing co-integration. Sometimes you can have some of them showing co-integration and others are showing no co-integration. But this one, we are lucky that all of them are significant, showing that there's a presence of co-integration. Okay, so let's run the other one. And this is Pedroni. So we have the cow and then the Pedroni. Let's run the Pedroni 2 and see. So the
Hello, sir.
Pedroni, please, you can talk.
Yeah, I'm not cutting so, but you see the cow co-integration test that you made mention that we are lucky that all those models are significant. So in case one of them is not significant,
Yes. So
it
like
will
I
mean that
said, like I said, always you just have to justify your results based on empirical study. But that's what I always use. You are not the developer of these models. Some people develop it. There have been studies published on it. So if one or two is showing co-integration and or one or two is showing significance and others are showing not significance, it means there's some form of co-integration in the data or in the model, just that maybe it's not strong enough. So you just have to assume there's co-integration. Then you justify that based on study published, which does that. And if you read enough, you will get a study that has similar results. Boss Eric, please, is that okay? Boss, is that okay? That's what I
yes, yes.
do. Yes.
Thank you so
I
much.
will assume there's a presence of co-integration. Maybe it is not strong enough, but you look for a study which is published who had similar results, mixed. So that one, it is a mixed co-integration result. So you just state that this maybe the Dickey-Fuller T showed co-integration, unadjusted Dickey-Fuller T showed co-integration. You justify that this study, blah, 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 had maybe a similar result and assume there's a co-integration. Or you can go and read about a study which also deals with the similar thing and use it to justify it. Because since one or two is showing co-integration, it means there's some presence of co-integration. That's why mostly it is better to run two multiple co-integration tests. Maybe if one is weak, one will show strong. Yeah, so this one, we can also check the Pedroni. Pedroni, you just change the cow to Pedroni. So XT co-in test, Pedroni, GDP, blah, 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 blah. Let's run Pedroni 2 and see. So, Boss Eric, you see here, there is the augmented Dickey-Fuller is showing weak, though it is significant because it is 0.09, but it is more close to 1. So it is significance at 1%. This one is significant, this one is significant. So let's say if the augmented Dickey-Fuller T this one was insignificant, we can use the cow test to justify why we have to assume there's a co-integration. So you can use one model to support the other if one is weak. And the same thing applies to the unit root and everything. You can just use one test, but to make it more reliable or to make your argument stronger, you can use like two models so that one will justify or will support the other or will provide some kind of robustness to the data or to your result. So this one too, the Pedroni also shows co-integration. That means there is a presence of co-integration in the data. There's a presence of co-integration in the data. Let's try the Westerland and see. So the Westerland, I know I'll definitely get error pair, yes. So the Westerland is saying that with lag 1, 0 leads, at least 23 observations are required. And my observation is 22. 22 observations. So it's saying that I cannot run Westerland. Let me see if 0 will work. Do you have 0 lags? So you see, when I use lag 1, it is saying that my observation should be at least 23 because lag means the 1 year will be taken off or one period will be taken off. So it will left with 22, which is not enough to do Westerland. So I changed my lag to 0. That means 0 lag. And then let's see. So we can see that none of them is significant. So you see, result for H2, the H2 is what? No co-integration, no co-integration, no co-integration. And then the p-value is 1.0. Who will interpret it for us? Who will interpret the Westerland for us? Who will help us? Zoom user. Who is Zoom user? Wanted wisdom. Mr. Adra, are you there? Interpret the Westerland result for us. Anyone to volunteer? We are having p-value of 1,111, 0.97. I think there's a robustness Westerland there. But that one will even be worse. Anyone to interpret it for us based on the null hypothesis?
Okay, Seth. So the now says that there is no co-integration.
Mhm,
The p-values are not significant.
mhm,
Therefore, we fail to reject the null.
So in conclusion,
There is no co-integration.
yes. So if we fail to reject the null hypothesis, that means, in other words, we are accepting the null hypothesis. And the null hypothesis is saying that there's no co-integration. So you see that the Westerland is saying that there's no co-integration. But the first generation, the cow and the Pedroni, is saying that there is co-integration. So this comes to personal decisions and also empirical literatures or empirical study. And the model you intend to use, you can report on this based on the model you are trying to use. You can also choose to report on these two if you want to use a long run or short run relationship model, like ARDL or something. But my personal advice is that if you intend to establish a relationship, a long run, then don't report on Westerland. Justify with a study that used Cow and Pedroni so that you can establish a long run relationship, then you write. If you also want to use only a short run model, then you can go ahead with reporting Westerland, that there's no co-integration. But I don't know, some of the reviewers, if they see that there's no co-integration, then they will get problem with you. One of our studies, we face similar problem. We ran Westerland, we reported that there's no co-integration. We ran our normal model, and then the reviewer saying that no, 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 no. And then he was giving us tough time to the extent of rejecting the paper. So nowadays, what we do is we look for a study that use Cow and Pedroni. Although there's cross-sectional dependency, we acknowledge the limitations, then we go ahead with that. This is a personal advice. So which one you want, you can go for. If anyone has a contribution to that, you are welcome. Anyone has contribution to that, the Westerland and Pedroni and the Cow. Okay, so I think 12 o'clock we will close. We have exceeded by 30 minutes. So we can report on the two. I will not report on Westerland. Westerland, I don't know why I've run Westerland like 50 times without getting any quantity. I don't know if I'm not running it well or something. I've watched videos and used the same thing too, but summarize the results into a table. Okay, so let's put our results into a table. So you see that AI is saying that there's co-integration, there's co-integration, there's co-integration. Okay, so let's report on our co-integration. I think we will bring today's session here. We will take questions. Then maybe in our next meeting, we will run the unit root test, and then we all decide on the models, or we will try and run some of these models. We will run fixed effects, random effects. Maybe if you get them, we can run Quanta, GMM, Discord, Cray, AMG, PMG, CCEMG, VAR, AFD, Wavelet. We have all these models. So in our next meeting, we will be running the unit root test. Unit root test to check the presence of unit root or stationarity of the variables. Then we will decide the models that we will all use. So let's present our cow test and then the Pedroni. And it is showing 9-3. 9-3. So table 4. Please, any question before we think our time
It's
is
good.
fast? Yes, please.
Thank you very much for this wonderful, series. I wanted to ask, first of all, that is there a way that, with respect to all the various codes that we run or all the various tests that we run, is there any possibility that we can get a means to copy all of them? I can see that we are doing most of them single way before we can bring them to the word. So is there any way that we can get all of them from the STATA at once, or always it has to be done in the single way?
Like
That's my first
you run
question.
everything, then you bring everything to Word.
Exactly. Like, is there any way like that? So this is the best way that we can go about it.
I don't know about that. I don't know. I know there's a command to export each result into tables. There's a command like that. Maybe I will show you in our next meeting. You enter it and it will export that particular result into a table for you. Then you will format the table nicely and put it inside. But to export the whole result that you have run to Word, then formatting it for you nicely and everything, that one day. I'm not saying it does not exist, but I don't know. What I know is you run the results, you either save your results to Excel and edit it nicely, or copy it as a table, send it to Word and edit it. Use the command to export it to a table and then format it nicely. Or you use this process, you copy your result, give it to AI to arrange it in a table for you. Then you arrange it nicely like this. You arrange it nicely like this. That's what I know. But there's no harm in studying. So we can all explore. I know STATA is very powerful and it's capable of doing a lot of things. So it can be possible. Any other question? If you have a question on the analysis we have performed,
Mine is a request.
okay, ma'am, listening.
Hello.
Please, we are listening.
After the meeting, can you kindly send the listen, the course, the one you